In this video, we're going to take a look at various techniques to determine whether a sequence converges or diverges. Many of these techniques are based off of techniques used to compute limits of functions. Recall that a sequence with a general term a sub n converges if the terms approach a single number as n gets large, in which case we write that the limit as n approaches infinity of a sub n equals L, the number that the terms approach. The sequence diverges to either positive or negative infinity if the terms get arbitrarily large in either the positive or negative direction, respectively, and we either write that the limit as n approaches infinity of a sub n equals positive infinity, or the limit as n approaches infinity of a sub n equals negative infinity. A sequence a sub n diverges if the terms approach nothing, and we say that the limit of the sequence does not exist. In particular, this third case where the sequence diverges essentially means that neither of the first two cases hold. The sequence does not converge to a single number, nor do the terms get arbitrarily large in either direction. The techniques discussed in this video will allow us to classify a sequence as having one of these three behaviors. The first technique that we'll discuss is the generalization of the limit laws of limit calculus to the world of sequences. In this case, we have two convergent sequences with terms a sub n and b sub n, respectively. And the limit laws say that if we combine our two sequences together using any of the standard operations, then the limit of our resulting sequence will be exactly what we would expect. For example, if we take our two sequences a sub n and b sub n and add them together, the limit of our new series a sub n plus b sub n will simply be the limit of the sequence a sub n plus the limit of the sequence b sub n. And the same thing is true if we subtract our sequences, if we multiply one of our sequences by a constant c, if we multiply our sequences, or if we divide our sequences, assuming that the terms and our limit of our sequence b sub n are always non-zero so that those expressions are all defined. In general, these limit laws allow us to break down the limit of a complicated sequence into some combination of limits of simpler sequences for which we can easily determine convergence. So let's take a look at a straightforward example of a limit of a sequence using the limit laws. Here we want to determine whether the sequence with general term 5n to the fourth minus n cubed plus 100 over 3n squared minus 2n to the fourth plus n converges or diverges. The term here for this sequence is a rational function, and what we really need to do is compute the limit as n goes to infinity of this term. There's a few different ways that we can approach this, but since we're talking about the limit laws at this point, we're going to use the limit laws here to compute this limit. Since the general term of our sequence is a rational function in terms of n, the standard strategy to use the limit laws to evaluate this is to identify the largest power of the variable n in the denominator. In this case, that would be n to the fourth. Once we've identified that, we want to divide every term in our rational expression by n to the fourth. The easiest way to do that is to multiply the expression by 1 over n to the fourth divided by 1 over n to the fourth. Of course, this is just multiplying by 1, so it's not changing the value of the expression, it's just changing the form in which it's written. When we distribute the 1 over n to the fourth to all of the various terms here, we get the limit as n goes to infinity of 5 minus 1 over n plus 100 over n to the fourth. And all of that will be over 3 over n squared minus 2 plus 1 over n cubed. Notice that the effect here of multiplying by 1 over n to the fourth, all over 1 over n to the fourth, is just to divide every term in the rational expression by n to the fourth. We now apply the limit laws, and we're not going to do so explicitly, but what would actually happen is that we now have the limit of a quotient, and so we would take the limit of the numerator and divide it by the limit of the denominator. And in each of the numerator and denominator, we have the sum and difference and constant multiple of various functions of n. And so we would end up here if we were to write it out in detail with 6 different limits to compute. The limit of 5 minus the limit of 1 over n plus the limit of 100 over n to the 4th in the numerator, and then a similar thing in the denominator. And each of those limits should be very easy to compute. For example, the limit of 1 over n as n goes to infinity is going to be 0, because as n gets larger and larger, 1 over n is going to have a constant over a denominator that gets large, and 1 over a large number will get closer and closer to 0. Same thing will happen with 100 over n to the 4th. Our numerator is constant, and our denominator is growing larger, and so the total fraction will get closer to 0. Similarly for 3 over n squared and 1 over n cubed. And so those 4 expressions all will go to 0 when we compute their limits as n goes to infinity. In a similar way, the constants 5 and 2 will have a limiting value of 5 and 2, respectively, since there's no n involved in those expressions. And so evaluating our limit, we get that this is 5 minus 0 plus 0 over 0 minus 2 plus 0, and that simplifies to negative 5 halves. And so the limit of our sequence, 5n to the 4th minus n cubed plus 100, all over 3n squared minus 2n to the 4th plus n, is equal to negative 5 halves. In particular, since this value of the limit is a number, this is a sequence that converges, and we would say that it converges to the limit of negative 5 halves. Another technique for determining the convergence or divergence of a sequence is the Squeeze Theorem. This is adapted from the Squeeze Theorem for limits of functions, and the version for sequences says that if we have 3 sequences, a sub n, b sub n, and c sub n, and each term of a sub n is less than or equal to the corresponding term of b sub n, which in turn is less than or equal to the corresponding term of c sub n, and the limits of the smaller and larger sequence are both the same number L, then we must have the limit of the sequence in the middle also being L. In other words, because the smaller and larger sequence of numbers are both approaching the same exact value, and the other sequence has terms that are squeezed between them, the values of b sub n have no choice but to approach that same number L as the sequences a sub n and c sub n do. The Squeeze Theorem is especially useful with functions that are bounded between certain values. For example, the sine and cosine function, which we know from trigonometry are always bounded between negative 1 and 1. In this example, we want to determine if the sequence whose general term is given by the formula 12 sine of n all over n to the 6th converges or diverges. When we look at the term of this sequence, the first thing that jumps out at us is that we have a sine of n in this expression. We know that sine of n is always bounded between negative 1 and 1 for any value of n. This is a standard property of trig functions. And we can use this as our starting point in order to use the Squeeze Theorem to verify our limit. What we ultimately need to do is get our sequence term in the middle of this inequality set here. And so we can do this in stages. We can first multiply the 3-part inequality by the constant 12, and we'll obtain negative 12 is less than or equal to 12 sine of n less than or equal to 12. And then we can divide each term by n to the 6th. And so we'll end up with negative 12 n to the 6th less than or equal to 12 sine of n over n to the 6th less than or equal to 12 over n to the 6th. And now we want to compute the limit as n goes to infinity of our first and last terms. On our first term, we have a constant negative 12 over n to the 6th. And as n gets larger and larger and larger, this term will get closer and closer to 0. The same applies for 12 over n to the 6th. As n gets large, n to the 6th gets large in the denominator, and so we have 12 over a larger and larger number, and those approach 0. And so here we have the exact setup we need for the Squeeze Theorem. We have our sequence a sub n sitting between 2 other sequences. Both of those other sequences converge to the same number L. In this case, that number is 0. And so the conclusion that we draw using the squeeze theorem is that the limit as n goes to infinity of 12 sine of n over n to the sixth must equal 0, and it's going to be by the squeeze theorem. So here we're not actually directly showing that our limit is equal to 0. We're showing that our limit must equal 0 by the squeeze theorem, and therefore this sequence also converges since the values approach a single number 0. Our next technique for determining whether a sequence is convergent or divergent is often called the continuous function theorem. And this theorem informally says that we can pull a limit inside a continuous function. More formally, if we have the limit of a sequence that is equal to a number L, and f of x is a continuous function at that particular value L, then the limit as n goes to infinity of the sequence f of a sub n is equal to f of the limit of the sequence a sub n. In other words, what we're really doing here is assuming that f is continuous, we're able to take the limit and put it inside a continuous function, and take the limit of the simpler function, or of the simpler sequence first, the limit of a sub n, and then evaluate our function at that value. In this example, we want to determine if the sequence, whose general term is given by cosine of pi over n, converges or diverges. We notice that in this example, we have a simpler sequence, pi over n, sitting inside of a function cosine, which is continuous at all values. And so what we will want to do here is observe that the limit as n goes to infinity of the inside sequence, pi over n, is equal to 0 because we have a constant over n as n gets large. And so using this, we're able to use the continuous function theorem since cosine is continuous at 0. So we really want to compute the limit as n goes to infinity of cosine of pi over n. And the continuous function theorem tells us that we can pull that limit inside of the cosine function. And so here we're going to have this equal to the cosine of the limit as n goes to infinity of pi over n. And so this here is our continuous function theorem. This is where we're using that in this example. We're pulling that limit inside the cosine function. Well, once we have that, we know that the limit of pi over n is equal to 0. And so this tells us our limit here is equal to cosine of 0, which is equal to 1. And so here we end up with a limit that is equal to a single number 1. And so this is another example of a convergent sequence. In this example, this sequence, cosine of pi over n, converges to the number 1. Our next technique requires us to think of our sequence as a function whose domain is the set of natural numbers. In other words, we want to define a function f where f of n is equal to the general term a sub n. If the limit as x goes to infinity of the function f of x can be computed using L'Hopital's rule, which involves derivatives, then the limit as n approaches infinity of a sub n will equal the limit as x approaches infinity of f of x. This equality here means a few different things. In particular, it means that if our limits are numbers, then the two numbers will be the same. If one of the limits will be positive or negative infinity, the other one will be the same infinite value. And if one of the limits is one that does not exist, then the other one will not exist as well. As a quick reminder about how L'Hopital's rule works for functions, if we have a limit of a rational function, so the limit as x approaches infinity of p of x over q of x, and it has an indeterminate form of either 0 over 0 or infinity over infinity, then the limit of our rational function p over q will equal the limit as x approaches infinity of p prime of x over q prime of x. Two quick reminders about L'Hopital's rule. The first is that we must have one of these indeterminate forms, either 0 over 0 or infinity over infinity, in order to use it. If we don't have one of these forms and we use this rule, then we could very well and most likely will get an incorrect value. The second is that when we compute the derivatives, notice that we're computing the derivatives of p and q separately. In particular, we're not taking the derivative of the quotient p over q using the quotient rule. We're only using the derivatives of the numerator and denominator functions separately. In this example, we want to determine if the sequence with general term a sub n equal n squared over 100 natural log n will converge or diverge. So if we go to compute our limit as n goes to infinity of this expression n squared over 100 natural log n, what we might notice is that in the numerator n squared, if n goes to infinity, n squared will also go to infinity. And in the denominator 100 natural log n, the natural log n will go to infinity as well. And so here we have an example of an expression with an infinity over infinity indeterminate form. And so we're going to apply L'Hopital's rule to this expression. Now this means that we're going to take the derivative of the numerator and denominator separately. And so the derivative of n squared will be 2n. And the derivative of 100 natural log n will be 100 divided by n, or 100 times 1 over n. This we can then simplify. This is the limit as n goes to infinity of n squared over 50. And as n gets large, n squared over 50 will get arbitrarily large, and so this limit is equal to infinity. So this example, this sequence, n squared over 100 natural log n, is a sequence which diverges to positive infinity. And we were able to justify this using L'Hopital's rule on the original sequence to form a new limit, which we were easily able to see diverged to infinity. The last technique that we'll discuss in this video for determining whether a sequence converges or diverges is often referred to as the absolute value theorem. This technique is often very useful when we have a sequence that involves an alternating sign, such as -1 to the n or -1 to the n plus 1. This test says that if we take the absolute value of our sequence, which effectively gets rid of our alternating sign, whether or not that limit is equal to 0 or not determines what will happen with the original sequence. If we take the absolute value of our sequence and we get a limit equaling 0, then our original sequence will also converge to 0. However, if we take absolute values of our sequence terms and the limit is not equal to 0, then the original sequence is going to diverge. Now, one thing that's important to note is that when we say the limit of the absolute value is not equal to 0, there are a couple different cases here that this could apply to. For example, the limit of the absolute value of a sub n could still converge just to a number not equal to 0. It also could mean that limit is equal to plus or minus infinity, or the limit simply doesn't exist. In all of these cases, the original sequence a sub n will diverge. In this example, we want to determine whether the sequence given by the general term -1 to the n times n, all over n squared plus 1, converges or diverges. When we look at this sequence, we notice that we have an alternating sign in our numerator, the -1 to the n. So this indicates that the absolute value theorem might be a useful approach for this particular sequence. In order to use that theorem, we're going to take the limit as n goes to infinity of the absolute value of our expression, -1 to the n times n over n squared plus 1. In this case, we notice the absolute value will eliminate the -1 to the n, since that will either be positive or -1, and both of those have an absolute value of 1. And so we simply get the limit as n goes to infinity of n over n squared plus 1. This limit we can compute either using the limit laws. We can divide everything by n squared, the largest power of n in the denominator, or we could realize that this is an infinity over infinity indeterminate form and apply L'Hopital's rule, in which case we would get the limit as n goes to infinity of the derivative of n, which is 1, all over the derivative of n squared plus 1, which is 2n. And we know that as n goes to infinity, 1 over 2n is going to get closer and closer to 0. And so the limit of the absolute value of our sequence is equal to 0. And so by the absolute value theorem, since that limit of the absolute value is equal to 0, the limit as n goes to infinity of our actual sequence is also equal to 0, and therefore this sequence converges and converges to 0. Now notice if this limit of the absolute values was equal to anything other than 0, say for example that it equaled 5, then the conclusion would be that our original sequence would have diverged.